Welcome back to Advent of Code 2015. We're up to day 19, and I might just manage to finish them all this session. I don't know. Do we think they'll get really difficult? We will see. All right. Let's begin. Let me turn this down a bit. Okay. Day 19. Medicine for Rudolph. Rudolph the red-nosed reindeer is sick. Oh dear. His nose isn't shining very brightly and he needs medicine. Isn't Rudolph supposed to be female? Yeah, because females are the only ones that keep their antlers in the winter, aren't they? So... okay, whatever. Red-nosed reindeer biology isn't similar to regular reindeer biology. Rudolph is going to need custom-made medicine. Unfortunately, red-nosed reindeer chemistry isn't similar to regular reindeer chemistry either. Oh dear. The North Pole is equipped with a red-nosed reindeer nuclear fusion/fission plant capable of constructing any red-nosed reindeer molecule you need. It works by starting with some input molecule and then doing a series of replacements, one per step, until it has the right molecule. However, the machine has to be calibrated before it can be used. Calibration involves determining the number of molecules that can be generated in one step from a given starting point. Okay, for example, imagine a simpler machine that supports only the following replacements: H to HO, H to OH, O to HH. Given the replacements above and starting with HOH, the following molecules could be generated. So in the example above, there are 4 distinct molecules. After one replacement from HOH. Alright. Santa's favorite molecule, ho ho ho, can become 7 distinct molecules. The machine replaces without regard for the surrounding characters. For example, given the starting H2O, the transition H to OO would result in OO2O. Sure. Your puzzle input describes all of the possible replacements, and at the bottom, the medicine molecule for which you need to calibrate the machine. How many distinct molecules can be created after all the different ways you could do one replacement on the medicine molecule? Alright then. This is just a straight... I mean, it's not a very long molecule, so it's just a straight... go through each of these and do every possible replacement and put them all into one big set. And then... okay. Well, 19. Alright, so first let's populate a dictionary of all of these. So read the input for each line. Okay. Hang on. So if line dot strip, if not line dot strip, we break out of this loop because there's one more line we want to read at the end, which is this. Okay. All right. So we want, what's this? So we want just a list of pairs. Let's say replacements equals list. So we want left right equals line dot strip dot split on basically this string here. Placements dot append just left and right. And then after this loop, we take one more input, which will be our molecule. Hang on. At this point we need hang on. If we need a boolean here, let's just say get molecule was false, bustle, false. If get molecule we don't want split, we want strip. Keep confusing the two. All right, and then all right. If it's an empty string, we set just break out of that. If it's an empty string, we want to get molecule. This is a bit more complicated than just reading the input. Shouldn't be this complicated. Okay. Otherwise, we just get the pairs. Okay. Does that work? Oh, so, yeah, that's true. If get molecule. Okay. Let's try running now. All right. we want, let's just print placements, print molecule. All right. If get molecule equals false. Ooh, that should be continue. Okay. There we go. Now what? It could take a lot of time. Well, okay, right. So, new molecules equals set. And now we just go for car S in replacements, right? For I in range length molecule. If molecule I is the same as car, that means it can be replaced. Then we do new molecules. We'll add the new string. Dot add. So it'll be S. So it'll be molecule up to I plus S plus, and then molecule I plus 1 onwards. And then we just want to print how many unique strings we have now in new molecules. So casing matters. It could be lowercase or uppercase. Oh! Damn it. You can have 2 string. Okay. We need to change this slightly. So it's not, change that to just word. Right, so for I in range length molecule minus length of word plus 1. So if it's 2, if it's a word of length 2, then we subtract 1. We start a bit earlier. So if molecule I up to I plus length of word is the same as word, there we go. Then new molecules add up to I replacement, and then we want molecule I plus length of word onwards. Five, 3, 5. Correct. Now that the machine is calibrated, you're ready to begin molecule fabrication. Molecule fabrication always begins with just a single electron E and applying replacements one at a time, just like the one-string calibration. For example, suppose you have the following replacements. If you'd like to make HOH, you start with E and then make the following replacements. E, O, H. Okay. So you could make HOH after 3 steps. Santa's favorite molecule, HOHO, can be made in 6 steps. How long will it take to make the medicine? What the oh my god. We cannot brute force this, can we? There's so many things you could end up with from E. We want the shortest path from E to this. What the heck? I think we have to do this the other way around. Find the shortest path from this to E. Because that'll stop us going down paths that don't yield anything. Yeah. Because if you start from E and try to branch outwards, you get so many different strings, it'll be ridiculous. It'd just be branching out. But if you start from this, the branching is lower from here. And you're always decreasing the string. It still would take a long time though, but then you got big strings like this, so it's breadth first search, basically. Interesting problem. Okay. Caca. Making poop. Titty. Right, so oh, I'm still on the browser. Okay, so I think we need a breadth first search here. So we want a queue for this. And put start in. We want a distance table. So we want to find the shortest path to E, working backwards. That's got to be the better way because there's fewer branches. All right, so while not q dot empty q dot get so we've visited this, so we've expanded current, right? It's already in dist. We expand it and we say if current equals goal, return dist current. So that's, we return the distance. Okay. Otherwise we get the neighbors of current. Here we have to write a new routine probably. Let's define get neighbors of a node. Let's call it X. So given the string X, we want to find all the neighbors. That means we basically have to do this again, but kind of backwards. So let's have a look at this. For word S in replacements, but we're working backwards kind of, but we can, okay, so we do that. For I in range, length molecule minus, so we want to change this to be length placements plus 1. If this, whoops, not replacements, S. If this molecule, the S length string is equal to S, then we want to yield molecule I plus word plus molecule and then S onwards. All right, so that gets us all the neighbors. So for neighbor in get neighbors of current, are they always going to be decreasing in size? Always. Yes, thank goodness. For neighbor in get neighbors current. So first thing we check, if neighbor already in dist, that means we've dealt with it before, so we don't want to go around in circles infinitely. Continue. All right, so this is something we've never come across before. So dist of neighbor equals dist current plus 1. Q dot put neighbor. We want to put that on the queue. And that's it. So then we just want the start, which is molecule, and the goal, which is E. Will that just work? None. We didn't find it. All right. All right. E is what we want, right? Yeah. It finished pretty quickly. Maybe it's supposed to, but let's print dist. So if we exit this while loop, something's gone wrong. We're not supposed to exit this while loop. But I think that's what's happening. Alright, let's have a look. So we've got the starting molecule. We're only finding a couple of neighbors. Yeah, there should be way more neighbors than this. For word, S in replacements. For I in range, length. Oh, molecule. I didn't even use X. X isn't the best variable name for this. Alright, anyway. Alright, now it's going to take a while. But I don't know of a faster way than this unless we use A star. It's still running. So if we used A star, the heuristic would be just like well, what is the longest replacement? It would be like from this to that. So basically we count how many. It'll be like that one. So it'll be basically the number of blocks of size that, whatever that is. Just divide the size by that. That's how close we are to getting to E. Yeah, this is going nowhere. Interesting. They don't normally need you to do better than BFS for these problems, but I mean, it's good. A star is a good thing to learn and use. Will A star even solve it though? Because it's still. Let's try it anyway. All right, so. Is there anything clever we can do here? I don't. I mean. We know that if we create... There are some letters here that we can never get rid of, aren't there? Okay, there's C, L, B... We can get rid of. CA we can... No. Can we? So CA, yeah, we can. F we can... H we can. MG, yeah. O, yeah. P, yep. Every letter here is possible to get rid of via another replacement, so this is not. It's not a speed up we can get from cutting out some of these. Yeah, I think A star is an interesting problem. All right, A star. Let's change this to A star. It can only help, right? Usually. So we want priority queue. So we want to find H of H for a given node. So I would say, so in general, what are the absolute minimum number of steps it would take to get you to E? Well, if we look at the biggest thing, it's like this one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that goes from 10 to 1. So basically squashes down by a factor of 10. So in theory... No, I'm thinking about this wrong. I should be thinking about this additively. Additively. It removes 9 characters from the string. That backwards replacement removes 9 characters. So basically, I should be counting how many characters are and divide by 9. How many times can we remove 9 characters until we get to 1, basically, is what I'm saying. So we say length x minus 1, take away the e, divided by 9. That's a float because it might and we want to round that up because if we have like 4 characters, that'll get us a float, and then we have to round it up because that still counts as 1 whole turn. So math.ceil of that. Alright, just turn that to an int. That is the heuristic. Okay, so q dot put. So when you put these in, you have to put the h value first. Don't need that dist table. Well, yeah, we do need the dist table. Okay. So while not q.empty, so we don't need the heuristic. Current equals q.get. So that gets the thing with the lowest estimated distance, because we're adding in the 0 here basically. And then if current is goal, again we return dist current. Yeah, that's correct. Hello, Sand Knight. Doing some AI coding. This one's quite a tough one, actually. Basically, you're trying to take this molecule. Well, technically, the problem was phrased, you're taking this molecule here, which is just the letter E, trying to build up that huge molecule via replacements, but I'm trying to go about this backwards because I thought that would be better. So take the big molecule and do the reverse replacements. I'm still not sure if that's the right... I think that's the smarter way to do it, because yeah, if you started from E and worked upwards, you'd make all kinds of ridiculous molecules which are nothing like that. So I think it makes more sense to take the bigger one and identify some of those strings, which are obviously some of these. Alright, so I think it's just a couple of steps I need to add here, so... how do I write A star? I've written this A star algorithm like a million times, but it always gets me stuck. So you take... Okay, so here, it's when we find the neighbors. So here, we don't do that. We don't skip any neighbors, because even if we found a path to a neighbor before, there might be a better path. So we don't skip any neighbors. Take that out. That's the difference between that and breadth first search. For neighbor and get neighbors. I might need to take a quick look at the Wikipedia on A star. Alright, let's have a look at this. I could actually bring this up. The number of times I've looked at this pseudocode, like throughout my whole life since I was a teenager, is huge. It's a bit different to how I do it. I don't normally create an F-score map because it's not that useful. Alright, so yeah, we don't want to reconstruct the path. We don't care about reconstructing the path. So while open set is not empty, for each neighbor, tentative G-score is the new... Yeah, okay. Yeah, let's follow this pattern slightly. So tent, dist equals dist current plus 1, like as the line below. If so if it's not better than what we've seen before, we skip it. So if neighbor not in dist, or what we currently have in dist is bigger, so we found an improvement, or tent dist is strictly smaller than the distance to that neighbor, then we update the dist of that new neighbor to be what we found. That makes sense. And now we need to put it in the queue. So queue.put, we use the H score. Okay. Right. That almost seems correct. There might be one or two infinite loops because... Alright, let's see. So we're only ever putting a neighbor in if it's better, if we found a better path to it than we've ever known before. So that ensures we don't... That won't be an infinite loop because it can only be a shorter distance each time. What else? So when we get current... Yeah, that will prevent that should prevent any infinite loop. I don't see any other infinite loop happening. All right, let's try running that. So will it actually run? Name BFS is not defined. Whoops. A star. Done! We ran in an instant. That is the beauty of A star. This is the key to video games. Like, it's the gold standard for AI pathfinding, because it's like, you either program your enemies to just try walking in random directions until they find you, or you program them to only ever take a step if they think where they'll end up is closer to you than it was before. That's the difference. It's not easy to code though. I get stuck every single time. But I always force myself to code it from scratch every time, because that's the only way you learn. Like, I never copy the code. 212. And if it's found a result, that must be the answer, because otherwise it wouldn't find a result. So I'm fairly confident this is correct. Correct. That was... You're a hard worker. I respect that from you. Well, also because this sort of thing comes up in job interviews. I've had this come up. And they make you write it in from scratch. Not only from scratch, but on a whiteboard. Which I don't really practice doing. Like, even physically using your hand to write on a whiteboard, that's something that takes practice. So, I'm completely out of my comfort zone. So I have to be able to code A* from scratch. Every coder needs to, really. Not that I've ever needed to use A* on the job. It's AI, so it's not always really needed in software engineering. It would be used in game programming, but not in the bulk of coding. I've not used my hands to write for many years, then had to write footnotes in the school book. I was like, yeah, I know, my hand feels weird. It was during the pandemic when I had to renew my COVID visa, my emergency COVID visa. I had to fill out like 2 or 3 pages of documents every month. It felt so weird. Like, there was a section where you had to explain why you think Thailand should let you stay another month, and I had to just write. See, the thing is, I couldn't just write because of COVID, because I want to make it sufficiently long so that the immigration officers can't even understand it, because they can't actually speak English. So I had to actually write in kind of complex English language. I feel that in the current climate, my safety is at risk, blah, 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 blah. I have to write several lines of nonsense just so that it's just too complicated for them to look up on Google Translate or something. And that basically was enough to make them go, okay, whatever, and stamp approval. It's like... So I actually, not only did I have to write stuff, I had to actually write, complex English. You sneaky git. I mean... Yeah, I had to play the system. I mean, Thailand benefited from us being there because we were the only ones, buying in the restaurants and all the stuff that the common people were trying to make a living from, like the massage therapists, the restaurant workers, all them. So it's just the government that was being problematic about letting people stay. So no regrets. I'd do it again. Alright, so we're on to 20. We're almost at the top of this mysterious image. Don't know what it's gonna be yet. We need those last few lines. Hey, I'm not judging. Yeah. No. Infinite elves and infinite houses. Okay, this sounds like a mathsy thing. Okay, this sounds like it might be something to do with the infinite hotel paradox or something like that. Oh, it sort of is. I can already see the Cantor's diagonal argument applying here. Alright. To keep the elves busy, Santa has them deliver some presents by hand, door to door. He sends them down a street with infinite houses numbered sequentially 1, 2, 3, 4, 5. Each elf is assigned a number and delivers presents to houses based on that number. So elf 1 goes to 1, 2, 3, 4, 5. elf 2. Two, 4, 6, 8. Okay, so you start from 0 and you add that constant every time. All right. Elf 3, so on. There are infinitely many elves, numbered starting from 1. Each elf delivers presents equal to 10 times his or her number at each house. So the first 9 houses on the street end up like this. So house 1 gets presents from elf 1, but never gets any presents from any of the others, because none of the others will ever reach house 1. So, although this is an infinite process, for every given specific house, there's a finite number of elves that will actually visit that house before no elves ever visit it again. Alright. So I can sort of see what they're going to ask here. What is the lowest house number of the house to get at least as many presents as the number in your puzzle input? So we need to find the lowest house number which gets this many presents. So first of all, do we really need this factor of 10? Can we just take a 0 off this input number? And instead of every house getting 10 presents, they get 1 present. I think we probably can. Not that it really matters. Okay, so... So there are a few ways we can go about this. One way, which will work probably, but I don't know if it'll be fast enough, which would be to just go house by house. For a given house, we can work out exactly how many presents it will get. We just go through the elves until we reach the elf with value like h plus 1. Because house 1 will be visited by elf 1, but it will never be visited by any elf after that. So we just, for each of the elves, 1, 2, 3, 4, up, to, and so on, we calculate how many presents they'll give. That's it. That's how many presents it will get. And when we get to elf h plus 1, we don't get any. And this is interesting because the number of presents we'll get will actually be based on the number of factors of that number. Yeah, house 69 will not be visited by any elves past 69. Yes, that's true. Hello, Amaro. You know what, Omara, the last problem I had, because we were discussing this before, the thing about A star, the last problem I had was solved by A star algorithm. Which surprised me, actually, because A star is actually considered advanced. I tried to solve it using BFS. It wasn't good enough. I had to upgrade to A star. They don't normally need you to know A star. But the problem was kind of basically... we're given a molecule, this big molecule here, and we're given a set of replacements. So every time you see an H, you can replace it with that, or with that, or with that. Every time you see an O, you could replace it with that, or that, or that. And the idea is, how many steps would it take to get from just the letter E up till that whole thing? And breadth first search is not good enough for this. You can't just try all paths. You have to smartly hone in on where the heuristic is guiding you. So that's actually, I would say that's an advanced problem. I mean, a lot of coders don't know A star, and every time I code it, I still have to look it up. So that was probably the hardest of the bunch so far. Alright, 20. We're on 20 now. So if say house 10, he will be visited by elf 1, elf 2, elf 5, because he's visited by every factor of that number. So the number of presents you get is 10 times the sum of factors, sum of divisors. Now, I think there's probably some quick formula for finding the sum of divisors. Sum of divisors, this is a known thing. It's the Euler function. The sum of all is that. Oh, they're just using the standard try every number. But you only try up to the square root of the number. Because if you go beyond that, you cover factors which are already covered before. So, for example, the square root of 10 is 3 something. So you only have to try 1 and 2. 2 will get you 2 and 5, because you know 2 is a divisor, and 5 is the corresponding divisor. But you never need to go off beyond the square root, because any numbers after the square root you'd have already covered before. So that's the speed up here. I think I'll just copy this. I mean, I know how to write this, but I could just copy that code there. So given a house, we know how to find how many presents it gets. So the algorithm would just be try each house one by one until we get a number bigger than that. These last ones are starting to go over my head. Yeah, some of them are clearly. This is number theory. This is you know, stuff you actually do at undergraduate level mathematics. So it is a bit on the mathsy side. So, all right, let me start coding. Because I remember doing this stuff in my first year of university, but we didn't do coding. So we were just doing everything by hand. I mean, we were still using blackboards, so we hadn't, you know, our university hadn't ever heard of computers. And they still use blackboards to this day. Blackboards are the best, you know. You never run out of chalk. It's very clearly visible against the blackboard, unlike, you know, colored pens. And you never have to spend the first 10 minutes of the lesson trying to find a new whiteboard marker because the current one has run out, which was basically what I had to do when I was a teaching assistant in my postgraduate university. I always had to run around the university trying to find markers which worked. Why is there a semicolon here? Get rid of that crap. Alright. Alright, so div sum. So define num presence for a given house. It's just, we get div sum. Oh, they're not counting, so they're starting from 2. So we need to add in the 1 and the, oh no, they already added 1, okay. Let me test this out. So print div sum 10 8.0. What? Oh, div sum. Oh, no, that's right. 1 plus 2 plus 5, except we also want the 10 as well. So I suppose just we're gonna override this and add the num itself, because the elf 10, yeah, 18.0. I think we want the, just take that as an int. 18. So that's right. 1, 2, 5, 10. Yeah, okay. So we want return is, we just multiply by 10 because they're giving 10 presents. So target equals this big number here. All right, so I'm hoping if we just go house by house, it won't actually take long until we do this. If it takes too long, I might need to think of using a sieve. Sieves are where you kind of have a big array of all the houses and you process them all simultaneously. It's a bit more complicated, but that's the technique for kind of more complex stuff. They're giving their number times 10 presents. So elf 10 gives 100 presents every house. So if I do this, I'd get 180. Would that be right? So you'd get, yeah, okay, right. So that's our target. All right, then let's just try this. H equals 1 while true. What exactly do they want us to give? They want to say the house number. Okay. If num presence H is greater or equal to target, print just the house number and break out of that loop. And now just increase H. Whoops. Oops. What am I doing? Okay, H plus equal 1. Alright. Just run it then. Yeah. I can't really think of a better way of doing this. And because I know of some advanced number theory methods which involve like Fermat's theorem and stuff, but they are quite advanced even for mathematicians. So I'd be surprised if they want us to do anything smarter than this, because even this is using the square root trick, which saves a lot of time. But yeah, it does look like it's taking a long time. I think this is probably a binary search. Yeah, a binary search will help here. If we know a number that's a lot bigger, we can just do binary search. We can, oh wait, no, that won't work, because it's not necessarily the case that each house gets more presents than the previous house. Actually, the number of houses can go up and down, so binary search won't work. Interesting. So then in that case, I don't know of any smart method of speeding this up. We can, okay, let's see how far we're actually getting here. If h is a multiple of 100, say, print h, and let's also print the number of presents as well. Let's see what's it actually getting up to. So we can cut corners by starting just from a later house. I mean, that doesn't look too bad. It looks like... Hang on. Let's stop it a second. Let's have a look. So we've got that many. 7 digits, and we're aiming for 8. So actually that might not be too bad. We just have to leave it running. So we can, okay, let's start from here now because we've computed that. I don't know. Well, it's not increasing much, is it? Oh, hang on. This is written incorrectly. That should be there. Okay, that will speed up because it won't be printing so much. Okay. Yeah. Okay, that's going faster now that I'm not printing so much nonsense. Okay, so it looks like it might reach it. It just has to run. We're almost into the... Oh, look, we're getting into the 1, 2, 3, 6, 7, 8 digits. We just need to get to the leading 3. Yeah, so sum of divisors, I don't think there is a faster way of computing that. I mean, I can look this up while we're waiting. I mean, you can do stuff with prime numbers. So there is a theorem which says the sum of proper divisors of n is equal to... But yeah, but you need to find the prime numbers. That's not much easier. So, but that probably is faster. But it's, I don't know much. But couldn't you start from target and work with its round divisor? Oh, that's interesting. So, hang on. So, yes. Well, the problem is... we found it. Okay, so what are you saying? You're saying start from target and... Okay, so the problem is that the divisors of that number there are very different to the divisors of, like, just adding 1 and 2. So, like, some of them could even be prime. So, although we could start from that target and that is a sum of divisors. So you'd have to find the numbers which sum to it, of which there are many. Yeah, I don't think that would be any better. I think that would just be more different branching. Alright, but it looks like this worked. 776160. So there is something which is faster, I think, which is to use the prime factors. It's a bit complicated though, and there's probably some code somewhere I could copy, but you'd have to find prime factors for lots of numbers and reuse prime factors you found before. Okay, that was correct. It's like how they encrypt. Might take a while to find out what will make. Yeah, this is the basis of encryption. If you put a bunch of prime numbers together to make a big number, it's very hard for someone to work out what prime numbers you use to make that number. And that is, nowadays we don't use that method of encryption because there are actually good methods for factorizing prime numbers, but it was the basis behind RSA, which is still used today, but just for very large numbers. But RSA is exactly that. Your encryption key is the prime numbers, and your encrypted number is the big number. Something along those lines. Yeah, so this is like the encryption. You take your message, you raise it to the power of E, and if you want to decrypt it, you then raise that number to the power of D, and you get back the original message. This is using modular exponentiation. And it involves prime numbers because modular exponentiation can be done really quickly if you know the prime numbers, basically. Yeah. It's also something that is believed to be crackable by quantum computers, because there's this algorithm known as Shor's algorithm, which only works on quantum computers, but it is known to find the prime factors with a probability of like 1 in 3. So you just run it 3 times and you'll probably get the prime factors. So, once we get quantum computers, that makes prime number based methods a bit less secure. But as I understand it, we're not really using prime number methods for very high security things. Even Bitcoin, some people theorize that quantum computers will crack Bitcoin, but it won't, because quantum computers don't speed up MD5 hashes, which is what Bitcoin is using. No, so Bitcoin is using SHA-256 encryption, I think, and that can't be sped up with quantum computers. Like that's a different kind of encrypting altogether. So quantum computers won't necessarily speed up that, but they might just speed up computing in general by a factor of like 1,000 or something, which does mean people with weak passwords are kind of in danger. People with strong passwords aren't. But yeah. Yeah, I haven't really looked much into quantum computing. Like, as I understand it, although we have quantum computers, they only have like a handful of like something like 6 atoms, which are representing the bits. So I should change my birthday password. Yeah, I mean that is one major issue, because a lot of these major corporations and stuff, at the end of the day, their CEOs are just putting their passwords on post-it notes on their computers. The easiest way to crack into major companies isn't using advanced algorithms. It's just calling up, Karen, who's the secretary of the CEO, and says, "Oh, I work in IT. I forgot my password. Can you email it to me?" or something like that. And then they just do it. Like that's social engineering, and that is the easiest way to to break into companies. That's how they do it. That's how the hackers get in. They just exploit bad policies. Alright, so the elves decide they don't want to visit an infinite number of houses. I don't blame them. Instead, each elf will stop after delivering presents to 50 houses. To make up for it, they decide to deliver presents equal to 11 times their number at each house. Okay. With these changes, what is the new lowest house number of the house to get at least as many presents as the number in your puzzle input? Ooh. This very much changes things. I used to test that for fun, where it worked, then gave a paper to the boss with their password on it and tell them to work their security out. Didn't make many friends. Yeah, that's... it's problematic because people who, like... people who do that, I guess to some extent it is considered a form of hacking and you should be a registered penetration tester in order to do that, but clearly these companies are not bothering with that security. So yeah, you're highlighting a major flaw, so it's kind of good that you're doing that. But at the same time, I can also see why it can be against policy to do that, because they can't have people going around doing that and then if they get caught they say, oh, but I was just penetration testing. I was just proving that your security is flawed, because it becomes an excuse that real hackers could use. But on the whole, it is good that you're doing it. But I also understand why companies can't make it allowable. Otherwise, everyone would just be breaking the passwords. But yeah, that's cool. Yeah, I support that. It was only doing social engineering, not computer skill. Yeah, exactly. The best hackers don't really need to know. Like, at the very minimum, a lot of hackers only really need to know some Python scripting just for stuff like this, you know, making some loops, checking values and stuff, but they don't really need to crack mathematical algorithms. Okay, so this really changes things. So the elves will stop after delivering presents to 50 houses. All right. Let me so this whole divisor thing no longer really works, because we wouldn't know whether the elf of that numeric value has already delivered all his presents before reaching that house. So given a house, we can't really for sure say, we won't know which elves are delivering to that house. So I think we now have to kind of do this elf process. Kind of step by step, like iterating over the elves rather than the houses. Wait, no. What I said is not completely correct. Okay, so an elf will deliver presents up until he's visited 50 houses. 50 houses, we know what that means. That means he's gone up to his number multiplied by 50 or something like that. Or maybe I'm one off. So, for example, yeah, so elf 1 will deliver the first 50 houses. Elf 2 will deliver 2, 4, 6, 8 up until 100. So basically, I think if we modify this div sum, we can say we can only add the divisors which are like less than or equal to 50 multiplied that elf's value. And all the bigger divisors we just discard. And this won't change the computational time of this algorithm. We still go through all the divisors. Hang on, let me think about this. So in the example of 10, house 10, we're looking at I equals. Well, it's not a good example because all the elves will still visit 10, but let's say 100. Go to house 100. So we look at elf 1. He won't reach this house because 50 times 1 is less than 100. We look at elf 2. He will visit this house because 50 times his number is at least 100. And all the elves after 2 will. I mean, until we get to the... Well, no, they won't. They will have the possibility to. Hello, Egretsu. In the interest of sharing info, in Python, x to the 0.5 is the same as math to square root x. Oh yeah, nice. Yeah, that is actually what I normally do. Is there any speed difference? I guess it wouldn't matter, but out of interest. Yeah, because this code I just copied from Geeks for Geeks. But yeah, I'm normally too lazy to type import math. I reckon the x star x asterisk 0.5 is actually in theory faster, but yeah, it is probably negligible. All right, so I want to override. I want to make a new div sum here, but I want to only count the factors which are so div sum every time we find a divisor, here's where we're adding the divisor. I just need to adjust this. So I'll say if it's if I times 50 is greater or equal to 100, isn't it? I mean, this whole thing could be rewritten easily, but I'll just keep it in line with how it was before. So if I times 50 is greater or equal to... No, not... Yeah, but 100 being... Okay, so none. Greater or equal to none. That means the elf won't have run out of presents. Interesting. So this actually massively... So we don't even need to check up to the square root. Instead, we should be checking from... Alright, well, let's just try it this way. If it takes too long, we can do a smarter checking which doesn't check up to the square root. Instead, it starts from the point at which I times 50 is greater or equal to num. Oh, wait. Why wouldn't I just... Oh no, because... Hang on. Yeah, no, there's a cleaner way of doing this. Just start from I equal... max to... So it would be what? Math.ceil num over 50. Because 100 divided by 50 is 2. So 2 is fine here, but later on we'll actually need to start from so actually this bit, we don't actually need the 2 in this max, we'll just leave it in anyway. Yeah, so we need the next integer value above that. The next integer, which is greater or equal to that divided by 50. Yeah, that's right. So we just start from there instead of 2. So it should be faster a bit, but in the higher numbers, probably not so much. No, it will. It probably will. Because that's linear. That's going to scale linearly. All right. So that's it. And then, wait, so let's call this div sum 2. And let's say num presence 2. We're also multiplying by 11. So that possibly speeds things up. H equals 0. So H equals 1. So while true. So we want num presence 2. This uses 2. Have I broken this? Why did I take this out? I forgot to copy this bit. Do we add... Hang on. We don't add 1 because none of these numbers will... Yeah, don't add 1. But num, you always add num. Because the elf with number num will always visit that house. Okay. So... Okay, try it. Can we just skip part 1? Oh, it's going up faster. 3009091. We'll see. I feel like I've done a bunch of things that I'm not too sure about. But in principle, I think that method is correct. It's just... Nope, it's too high. But yeah, I don't think I've coded it correctly, so... I mean, the key is this div sum. Well, okay, first, let's assume div sum is correct. So, num presence 2 would do 11 times div sum 2. Would that be what we want? Yeah, 11 times... Okay. So it's all down to this diff sum. So what did I change? So now I'm starting from I equal num divided by 50. Wait. No. Why am I dividing by... Hang on. No, that's not right. Why did I divide by 50? That's just the case of 2. No, it's not divide by 50. What is it? So... No, hang on. So let's say I equals... so num is 1,000. Where do we start from? Which elf do we start from? Is it 1,000 divided by 50? So, 20? So elf 20 will deliver to 20, 40, 60, so on. Up to 1,000. Yeah, you do. You start from... We don't need this max bit, that's not necessary. You start from num divided by 50. If it divides cleanly, then we want that exactly. If it doesn't... then we start from the next integer up. Yeah, house 3250 doesn't work well. So with this sum, it would be 32 divided by 50 would end up being some fraction that would round up to 1, and then it become an int. So that would start from I equals 1, which will be fine here because that will include all numbers will be valid because all elves could still have their presence by that time. So, but we can also just start from like h equals 50 or something, because we know we're not going to get that many presents from earlier. So all right, so I think the starting point is correct. And then what? While I is less than or equal to... Oh, these numbers look suspicious. No, that is not right. They're too regular. No, I think I'm... hang on. I'm capturing... $85.50 would round down to 1 or something, and when rounded up or down 1 or 2, which those two elves do not visit 85. Hang on. Okay, so 85 will be 1 point something, so it rounds up to 2. So we start from 2, but we still do this factor check. So we start from I equals 2, and then 3, then 4, then so on. But we still do this factor check to see if it's a factor of 85. So the factor check is what's checking. So if we get to I equals 5, it should count that. But the problem might be in this factor check. I don't know if I'm... Alright, yeah, but I mean, we should actually test some of these smaller values, so... Let's comment that out. Print num presence 2 of 10. Start with 10. That should be the same as before. 308. No, it shouldn't be the same as before. Should be... So before it was multiplied by 10, now multiplied by 11. Igretsu, the... I regret Zu. The explanation is... Okay, so the problem is this here. In fact, I can also drop the link. But if you go to that link, you won't see part 2 because it's unlocked. But it's basically part 1, but then we change it slightly. 198 should be the answer to 10. You might be right, yeah. So yeah, this is wrong. It is way too big either way. So before it was 180, so it'd be 18 times 11. So yeah. So what's going wrong here? So 10. So we start from I equals 1. Well, for these small numbers, probably we do need to keep that in there. And also if num is less than or equal to 50, then we add in the 1, because elf1 will reach the house if it's less than or equal to 50. So we'll say result plus equal 1. Alright. Otherwise we don't add the 1. Alright, let's try that now, see what number we get. 198. Okay, so it seems correct for 10. It's kind of hard to check higher numbers. We could try 100. Just see what the number looks like. 2376. But then 10 doesn't have any exclusion compared to before. Yeah. Yeah, that's trickier to test. I mean, we can test the example they've given us in the Oh, I didn't have the IDE showing then. Oh, they don't have any. They don't have an actual example here. Normally they have an example. Okay, so we have to do this on our own. Okay. So the starting point here is correct, I think. We start from the point at which the elves can actually reach it in time before they run out of presents. And the only things I changed here was... well, nothing. The only thing I changed was the starting point. So, do I need to change more? So, for example, for house 1000, we start from 20. That sounds about... yeah, that's right. And we... So num presence 1 for 100 was what? Oops. 2170. Num presence 2, 2376. What if I were to just change this back to 10? How does that compare? 2160 compared with 2170. So for 100, we've taken out 10. So we've excluded. So when does a house even get its first exclusion? That number's got to be quite high, actually. Well, yeah, 51. I mean, I can test 51. So let's test 50 first. So I'm keeping it as 10 for now instead of 11, just so the numbers are easier. So this should be... So it's saying... Oh, that's the old algorithm. That's 93. So the sum of factors is 93. All right, so now we switch to the new sum of divisors, new presence. So it doesn't change. That's what we're expecting. 50, it stays the same. Now 51. 710. And for the old algorithm, 720. So we basically remove 1. Remove 1, literally elf1. That's correct. Okay. And let me look at the result again. Let's put 11 back. Yeah, no, something's not right. It should be wavering all over the place. Why is it so consistent? So if I were to change this back to 2, that's basically what we had before, isn't it? So what will happen now? Now it goes all over the place. Interesting. So who even goes to 51? 1 to 3 and 51, and then 1 doesn't go. So it's what's 17. 51 divided by 3 is 17. So you would have 3, 17 and 51. Seven, 8, 1. Wait, so that's with still multiplying by 10 or multiplying by 11? Oh no, so that's sorry, that's so let me put, okay, multiplying by 11. 7, 8, 1, yeah. So maybe, okay, so it looks weird that it's so consistent, but maybe that's correct. that it's supposed to be consistent. But I think the number is probably just slightly off or something. It's weird because there shouldn't be that many changes to this. It's literally just cut off the elves at some point. So I claimed it was that 3009091. And that is the H value it's saying, 3309900. I should also print this. Okay. Let's just see what the result they're claiming looks like. We can test this. Test whether this is... So they're saying 3009091. That seems odd. Okay, so we can find out what the factors of this are by just, I don't know, Googling it. Factoring calculator. No, not factorizing expressions. Find all divisors. Okay, here we go. So type in our number. Trying to find it. Okay, I don't know how to use this. Ah, here we go. No, what? Ah, it says it's prime. Yes, that number is prime. What? So that is very wrong then. What? That's prime. Oh. That means we're only ever adding num for some reason. Wait, what? So we're doing 11 times that. Is that? Three, three, one, oh, yeah. we're literally only including the... is that... I mean, that could be close to, well... okay. So we need to find an example here that is wrong. So that's right for a prime number. The problem is the ones before it probably are wrong because they should be having more factors which go up above the target number. So that is a prime number. Oh no, this is this is just normal for these adventive codes. But it's probably a very small error somewhere because... Alright, so let's have a look at this. 300900. That clearly has lots of factors. So let's find the divisors of that. Whoa, okay. 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 17, 20, up to... What the biggest factor is 1504500. So, according to our divisor method, we should be starting from 300900 divided by... Oh, I'm starting to see how this is different, but okay, so that number 30090000 divided by 50 is 60,180. So we should be starting from 60,180 and only taking all the divisors above that. Yeah, there's definitely a problem here because there are divisors above that. Why are we not adding them in? Oh, it's because... Okay, I see the problem now. It's because this div sum we were using is being clever, and it's only going up to the square root and not the full number. So the idea being, if you take a small number, which is smaller than the square root, there'll always be a corresponding divisor, which is larger than the square root. So you can add them in pairs, and that's smart. But the problem is, if there are small numbers which are underneath our threshold, we're ignoring them. But in ignoring them, we're also ignoring their pairs, which are larger than the threshold, because we're only taking the smaller numbers. We're only ranging through the smaller numbers, and we're always adding their corresponding divisor with them. So there are some cases where there are large divisors which are higher than our threshold here, which we want to capture, but we're failing to capture because their small partner was below the threshold. So actually, we can solve this by getting rid of this, just going the full range. Or to go to that, actually, because we're adding in num later on. Now, that is going to be slower because we're going up beyond the square root. But because we have a threshold, it might actually be pretty fast anyway. All right, let's try that. Okay, it will take a while, but we're probably... I mean, this might be correct now because there is a speed up here we can do though, because the largest factor we can possibly have is is the number divided by 2, isn't it? So we should actually go like this, num over 2, not the square root. So that will make it twice as fast, surely. I can't think of another speed up there. Let's just see what happens. Yeah, it was suspicious how consistent it was, but yeah, that's why. It's pretty slow, but I can't think of any. Oh, there is a way we can speed this up. We can still do that. Wait, no. We can still do that square root thing, but instead of starting from the threshold, we look at the I and the corresponding num over I, and we add each of them into the sum, depending on whether they are valid or not. So actually, yeah, that is the way of speeding this up. Let's see what happens though, because it looks like it will actually finish. 2, 3, 4, 5, 6, 7. No, we need to get to 8 digits. All right, hang on. Let's do that. So this is the correct way to do it, I think. Get rid of this. We start from I equals 2 again. Actually, go back to the square root. Wait, why have I got these brackets here? Okay, so yeah, why are these brackets here? Okay, take that out. Start from 2. We should be starting from 2. When we get to this point here, we find the divisor, we find its partner. We say if I is greater or equal to, or if 50 times I is greater or equal to num, then we do this. And then here, and similarly, if 50 times num over I there. That should be only adding in the factors which are valid. And then we're adding in 1 if. Yeah, I mean that's not important. We're not going to be dealing with small numbers. And then we're adding num as well. Right, let's try that. I should have tested that on the number we know. Okay, so that's going way faster. Because that goes from a linear factor to a square root factor. That's all right, we're getting big numbers now. That's how I should have coded it to begin with. I was beginning to code it that way, and I was thinking, oh hey, we could skip that and just create a threshold here. But yeah, that was wrong. All right, we're in the 8 digits. We just need to get to 3. 3 as the leading digit. So one of the things that's kind of, well, for these problems, they give everyone a different input number because that makes it hard to cheat. You can't just copy the number someone else has used and get the same answer. So they give you different numbers. So my number was this. The problem, though, is clearly that if they're giving different target numbers to different people, and they're taking this approach, starting from 1 and climbing upwards, then this is kind of unfair towards people who have higher targets, right? Because it's going to take longer. I don't know how this was handled in the competition. It could have just been something that was considered unfair, and so be it. But yeah, if you've got a bigger target number, it's going to take you longer, and therefore you're less likely to reach the top 100 because speed is of the essence. You know, you're competing with people who are going to complete this in seconds to minutes. All right, so they're saying this is our answer. All right, this looks sensible now. The number is going up and down. Yes. Okay, that wasn't actually a hard problem. It's just the textbook deviser's method. I tried to cut corners there. All right, we're up to 21. Almost done. I don't know if I'm gonna manage to do it this stream. Maybe. RPG simulator. Little Henry Case got a new video game for Christmas. It's an RPG. Yeah. In case you guys don't know what RPG games are, they have a handy Wikipedia link. A role-playing game. It's a video game where the player controls the actions. But and he's stuck on a boss. He needs to know what equipment to buy at the shop. He hands you the controller. This is a controller. Could there be anyone doing these programming competitions who doesn't know what an RPG or a controller is? Seriously, there's a huge overlap between people who do these programming things and people who play video games. There. Or who at least, you know, are integrated into geek culture and know about video games, even if they don't play them. In this game, the player, you, and the enemy, the boss, takes turns attacking. The player always goes first. Each attack reduces the opponent's hit points by at least 1. The first character at or below 0 hit points loses. Okay. Damage dealt by an attacker each turn is equal to the attacker's damage score. I used to do charts about that kind of optimization when I was young. Oh, really? Yeah, this is very much like what you would actually code into an RPG game. All right, so except of course if it were a Japanese RPG game, you'd multiply all those numbers by 100,000 or something. Damage dealt by an attacker each turn is equal to the attacker's damage score minus the defender's armor score. Okay, attack minus their defense, essentially. An attacker always does at least 1 damage. Okay. Your damage score and armor score both start at 0. They can be increased by buying items in exchange for gold. You start with no items and have as much gold as you need. Your damage or armor is equal to the sum of those stats from all your items. You have 100 hit points. Here is what the item shop is selling. Leather armor, yeah. Okay, so we've got cost factors here. Wait, you have as much gold as you need. So why does the price matter? Okay, we'll find out. Oh, I see. We got rings, which, okay. Excuse me. So fine. You must buy exactly one weapon, no dual wielding. Armor is optional, but you can't use more than one. Cheapest way to win. Yeah, it would be optimizing something. Yeah, it is the cheapest way to win. Armor is optional, but you can't use more than one. You can buy 0 to 2 rings. At most 1 for each hand. You must use any items you buy. The shop only has 1 of each item. So you can't buy, for example, 2 rings of damage plus 3. Okay. For example, suppose you have 8 hit points, 5 damage, and 5 armor, and that the boss has 12 hit points, 7 blah 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 blah. Okay, I know how this works. Okay. And we can optimize this. We don't have to play out turn by turn. We will know exactly how many turns it will take to kill the boss. It's a straight up division. So that will bring that from linear to kind of constant in terms of number of steps to work out who wins. So you have 100 hit points. The boss's stats are here. That's our input. Okay, cool. So we want the least amount of gold we can spend. Boss stats are this: 100 hit points, 8 damage, 2 armor. If you manage to calculate this by hand before I programmed it, I'm using your your result. That's totally legit. Like, actually, that's I mean, that's even encouraged if you can find ways to solve these without using code. Like, by all means. But I'll continue coding this. Yeah, no, I'm saying if you do manage to solve it, I'll take your answer and just plug it in. I'm not even going to bother coding it. Like, I'll take any shortcuts I can take. So yeah, I'm happy for you to actually find the answer if you can. I would do the same if I can find the answer without coding. So if I would, so what would seem about right here? Wait, he's got the same hit points as us. That's convenient. Okay, so he does 8 damage and he's got 2 armor. So, and we've got 0. Okay, so you would think that we would want at least his stats, but you might want more damage and less armor, or other way around. I don't know. So how much would it cost to match him? Like, we could get a dagger. Wait, no, to match him, we could get a great axe to do 8 damage. We could get like a ring. No, a chainmail armor, which is cheaper. So, and we go first, so we would win because we have the same stats as him. So Great Axe and Chain Mail is 105 gold. So the question is, can we beat that? Can we just do this in our head? So what would happen if we switched to short sword? Because that's long sword and ring 1 is cheaper. So go all in on the damage. So long sword and what is that, damage +1? So just go all in for the damage. Interesting. So that's what, 65 gold. If we calculate the number of turns needed to kill the boss and the number of turns to lose, we could probably brute force it by grabbing the next cheapest item iteratively, right? Yeah. Yeah, that's basically the code. The code is pretty straightforward. I'm trying to see if we can... But yeah, so how many turns does it take for the boss to beat? Oh, well, it depends on our armor, so... So the best found so far is what, longsword and what was it that Amaro said? Ring +1, 25. That's pretty cheap. 65 gold. Longsword +1 deals 6 damage, he deals 8 back, you'd lose. Yeah. Wait, so... Yeah. Oh, I think Amaro meant just for the damage. Then Great Axe. Oh yeah, good point, yeah. Okay, so it's longsword, damage +1, and chainmail. Yeah, that is true. So that's cheaper. So it was what, 65 plus 31, so that's 96. Great Axe is never worth it, yeah. That's true. Well, unless you have too many rings on. Unless you have too many, unless you just want to wear defense rings, but I don't think you would. So what was that, 96? So could you ever get away with something as cheap as a dagger or something? Because that would do only 4 damage, so you would need... Alright, I might just start coding it, but... do we think we can beat 96? If your armor was high enough to win by attrition. So they're doing 8 damage. So if you can get like 8 armor, then they'd only do 1 damage, wouldn't they? But that already costs more. So 4, 5, 6, 7. Well, if you had 7 armor, they'd be doing 1 damage to you. But that's 75 and... Yeah, it looks like armor is not really worth buying. Well, not big armor anyway. 53. Alright, I mean, you can try as many times as you want, so I could actually just try that. You could guess 90. So what was the question? What is the least amount of gold you can spend? Well, 6 armor gives you 50 turns to kill, and 5 armor gives you 33. So how do you make 5 armor? Either plate mail or... But yeah, that already costs... Well, that costs 93, and then you need to buy something... Yeah, that already costs more. So that already is not more optimal. All right, let's try 96. Wait, is that right? So it's 40, 65, 96. All right, let's try that. Not the right answer. And it also doesn't tell us higher or lower. They know that it would help us too much. Oh, no, I'm being stupid. Of course, we know it's going to be... Well, no, if we know that it's a valid purchase, then yeah, we know it must be lower. Okay, fine. I'll start coding it. I'll probably need this for part 2 anyway, so we don't need to extract the input here. We can just hard code that. All right, let me switch to... So clearly we have to buy a weapon, or we can't do any damage to him. Do we have to buy armor? If we were to get the best weapon and the best attack, can we beat him? Let me create a new... Maybe not. What would happen if we went all in on an attack? So you could actually buy 2 rings, can't you? So you could get... But that's already more expensive, so... Great Axe. Yeah, we already established Great Axe isn't worth it, so yeah, so we can just... In terms of coding, we can specify you have to buy a piece of armor, I guess. And the rings are more expensive in terms of defense than the armors are, so... So yeah, it makes sense that you have to buy armor. Because anything without armor, you would need a Great Axe or something, which would cost too much. Okay. How do we code this? See, the real input that matters here is this, not the... Hang on, let me copy this. Or I suppose I could hard code the weapons and armors and stuff in. Yeah, it's not that... It wouldn't take that long to hard code it. Alright, so... Let's define... Is a win given attack given attack and defense. Can you link shop address? Yeah. Oh, we can't use def. All right, so my HP 100. It doesn't, I mean, they're both 100, so we can just say turns, my turns, this is how many turns I take to kill the enemy, equals how many strikes I take to kill the enemy. It'll be 100 divided by hang on, so if it's, so what I said earlier wasn't quite true. You can if you strike with no weapon, you still do 1 damage. It's said you do a minimum of 1 damage, but I'm pretty sure that that would be pointless. All right, so it'd be 100 divided by, so it'd be my attack minus their defense, which is 2. But I need to take the minimum of that on 1. They said you need a weapon, but if it would deal 0, it still deals 1. Okay. Either way, we couldn't beat him without a weapon. Yeah. Alright, so minimum, so maximum of 1 and attack minus their armor, which is 2. With 8 armor, you... Oh, right. Okay, so so it's that. We need to seal it because yeah. Might need to use at least 1 more turn to finish them off. So, is that right? Attack minus 2, their armor is 2. Yeah, that's how many turns it takes for me to get them. Enemy turns equals just the other way around. So 100 divided by max 1. Their attack is 8. My defense is that. If my, it's now just return my turns is greater or equal to enemy turns, because I get the first turn. Sorry, my turns is less than or equal to. Less than or equal to, no wait, we're allowed 1 extra turn, aren't we? So hang on. +1. So if we can kill him in 2 turns and he kills us in 1 turn. No, that's not right. No, yeah. My turn's less than or equal to enemy turns. Okay. Now we just want to create a table with all these costs and damages. All right, weapons equals we don't need to even name them, just create a list of tuples. So we've got cost, so it'll be 840 1050 2560 4070 I'll just put Great Axe in anyway, even though we've sort of determined you never really want to buy it. 74. Probably need stuff for part 2 anyway. 0. Armor. $13.01. 13.01. 31.02. 53.03. 75.04. The hardest part, the longest part of this is just extracting all this. 75.04. I could have paused that, but I don't understand. Are these tab characters? No, they're not. Yeah, I don't like the format they've given this shop in. It could have been comma separated or something. 75.04, 102.05. And the rings. So 25.1. 52.0. I should have, I don't know, pasted this into Excel and then taken it out again. That probably would have given me a table I could have. 103.0. 20.01. 40.02. 80.03. All right. So what the rules say, you must have exactly one weapon. Armor is optional, but you can't use more than one, and you can buy 0 to 2 rings. So there's a hack we could do here. We could actually add a dummy armor. 0, 0, 0. So we don't have to separately handle the case where we don't put on an armor. We can just say that is an armor we can buy for 0. Same for the rings. We can have 2 dummy rings. 1 for each hand. Like that. Alright. Yeah, it makes the code... Then you don't have to do an if this, else this. It makes the code way easier. Now, it's just one huge for loop, so... Best equals the best cost we found so far. Let's say 1,000 or something, just to start off with. For W in weapons. For armor in armor. Well, so they said we can't buy duplicate rings, right? You can't buy, for example, two. Ah, okay. So here we just need to... Either we use the permutations library, or we could pop it. I don't want to mutate these lists. That'll get messy. We'll keep them immutable. Just say I could use permutations library, or just do this. Just say for I in range length of rings, -1 for j in range. So this picks an index, and then j will always be an index after this ring. For I +1 up to length of rings. So that picks 2 rings, and it's I is not allowed to be the last one, and j is not allowed to be I or the previous ones. So it's always kind of picking them like that. Random.choice. Yeah, but that would be random. So we don't want random, because we wouldn't know when we've covered them all. That'll just take a random pick, and we'd have to do it like over and over again until we know. We would never, technically, we'd never know until we've got every possibility. So this one ranges over them. So ring 1 equals rings I. But yeah, the library I was thinking of would be iter tools permutations or combinations without replacement. That's probably quite easy to use. I just couldn't be bothered to import it. Ring 2 equals rings j. All right. So we've got all of these. The total cost equals plus a, it's the first element of each. I'm still trying to use this right shift on my keyboard because I've broken caps lock and left shift. And I'm down to 1 remaining shift. Can't get used to it. I've got my whole life using left shift. All right, even using caps lock was difficult for me to adjust to. I remapped it in the registry. Okay, so the cost is that. My attack will be that. I mean, armor doesn't contribute, well, we'll just define it like that anyway. My defense will be that. If is win, this attack and this defense, then best will replace best with the better of the old value and this cost. It would have been faster to go straight to part 2 in case you don't need to code anything. I don't know what you mean. I can't see part 2 until I've beaten part 1. Right, this will just print the cost. See if you can work out from the cost itself what the components were. But I can print the components. Let's see. 91. So we can beat it in with 91. 93 is your answer. There are only like 2 cheaper options that it can be. Well, we didn't find them in this time, so probably was faster to code. Alright, 91 apparently is the answer. Let's see if that's correct. And then from that, see if you can work out what the components are. Let's check if it's correct though. Okay, it's 91. So that'll be like... Alright, I'll leave you to think about it for a bit, but I can just... if we can't figure it out, I can just print out what it was finding. Let's have a look at part 2. I'm just going to get a bit of tea as well. $31, $10, and $50. So what? Chainmail, short sword, and damage +2. So that's 7 damage. Does that work? Interesting. Longsword would be the same damage for cheaper. Well, it's not quite because... wait, sorry, longsword is... Yeah, longsword is cheaper, isn't it? Hang on. That does sum to 91. Wait, so would... Yeah, well, how does that work? Wait, so, okay, so that would be 7 damage either way. Yeah, 7 damage wouldn't work, would it? No, because the extra turn, there'd be more than 1 turn lost. Yeah, I don't think that would work. But that does sum to 91. Alright, what have we got for part 2? Turns out the shopkeeper is working with the boss and can persuade you to buy whatever items he wants. The other rules still apply, and he still only has one of each item. What is the most amount of gold you can spend and still lose the fight? Interesting. Most amount of gold, which will cause us to lose the fight. It's probably spending a lot on the armor. Like, for example, if we spent 100, if we bought plate mail with defense, that's already still losing. So I worked out how much it costs to increase a point of either defense or attack, targeting reaching 10 points, which would equal boss stats. Oh, let me just get my tea. $230 maybe this time, so that's like what was boss armor? Boss armor is 2. Eight attack, 2 armor. Alright, I'm gonna start coding this. Well, should we look at what the answer was for that first part first? Let's see. So, if... Let me rewrite this. If best is... If cost is smaller than best, best equals cost and print WA ring 1, ring 2. Alright. So the last time it changed was if we have, so it was 40, 31, 20. Let me have a look at this. 40, 31, 20, and no second ring. Longsword, chainmail, and defense +1. So that's the optimal amount, apparently. Yeah, I mean, yeah, I guess your technique, yeah, it would have worked. It's kind of linear. So you can attribute gold to damage and armor points. It can get a little bit tricky around the point at which you're doing 1 damage when instead of like negative damage or whatever, like that makes it not completely linear, but yeah. All right. I see. Okay. Cool. All right. So part 2, I think is just we just reuse this. So part 2. So I want to say trying to make the most cost where I lose. So best equals, let's say 0. And I say if not is win. If cost is greater than best. Print best. Let's hide that for now. Anything else I need to do? So yeah, we lose, and we want the better cost. All right. 158. Amaro, was 163 a valid one? Because it could, I mean, it could be wrong, this program. How did you get 163? All right, I'll test this out. Yep, it's right. 158. So how do we get 158? By cheap weapon and armor. So, and then rings. So yeah, you probably want to get 2 rings. So probably you want defense 3 ring. Or not, I'm not sure. Yeah, so you have to have daggers, so you're doing at least 4 damage. Was it 158? So probably 8 from dagger, so what, 150 from here? So like damage 2 and damage 3. Let's print out, let's see what it said. So yeah, that's the dagger, no armor, and the 50 ring and the 100 ring. Yeah. Makes sense, yeah. And what you're describing there, Sam, like your process of equating the values to like a per gold value is sort of the basis of what is it called? Well, linear optimization in general, but there's a method called the simplex method or something like that. I don't know. Linear programming, it's where you have these set of constraints, like each of these lines is kind of your constraints, and you want to try and find the optimal amount. But trying every value is expensive. So if this was a huge table of values, we wouldn't want to try every possible combination. We'd have to be smarter. And so we would look at sort of like looking at this approach basically. It's expressed mathematically, but it's sort of similar to what you were doing. Yeah. There's a lot of research done into these types of methods because this does come up in a lot of real life scenarios. All right then. $22. Trying to think. I need to get to the supermarket, so I think I might have to finish there then. I'll leave the 4 problems till next time. That might be a couple of days away. I'm flying to Vietnam tomorrow. Well, tomorrow late in the evening. And assuming I can get good internet in Vietnam, but I probably will, because Vietnam is way better than India in terms of internet. Well, Vietnam and Thailand are both like really very strong internet countries, so I shouldn't have any problem. And yeah, 4 problems, that'll probably take up a full session as well. Traditionally, 25 is usually an easy-ish problem, because they don't want people spending all day on Christmas Day, which they totally would. If it was that, if I'm stuck on a problem, I am spending all of Christmas Day on that problem. So they usually make 25 a sort of easy-ish one. But last year, I would say it was actually a little bit tricky. It didn't take long to code, but I wouldn't say it was easy. It was kind of, you had to think about it very mathematically, and it was kind of hard to get your head around it. It's like changing decimal to this made-up system that the elves use called Snafu. It wasn't easy, but it didn't take long to code it. But there was no part 2. Part 2 was you had to get all the stars for the previous days, and that was your part 2, which is funny. Which I think is what he does every year. So part 1 is just to do that, and then you only get the part 2 star if you've got all the stars for the previous days. Alright, and also, if anyone who's watching wants to join my leaderboard for this, it's just a fun thing to compare which stars you've got and stuff. Then you just have to copy that code there, type it into the site. I mean, yeah, it is mainly for coders, although clearly some of these problems can be solved by non-coders, so without coding, so you can do it that way too. And then I just have to complete 2016, 17, 18, 19, and 21, just in time for this Christmas. That's just going to be my full-time job this year. And then 2023 will start on day 1 of December. Yeah. While the rest of the world are enjoying their Christmas holidays, we programmers will be busy with this advent of code, stuck for hours. That's how it goes. Right. I might jump into some Azure Dreams later if I have some time. It might be my last chance to have another stab at 100% before I have to move. Alright. Well, thanks for watching, San Knight and Umaru, and thanks also for I Regret Zoo for dropping by. And yeah, I'll finish this off maybe in 2 or 3 days.